All right, so for day 2, so it says 6.3, it's actually day 1, but our second day of in this module, it says, remember if two figures are congruent. We dealt with congruency a lot right before break in that geometry module, module 6. Obviously, you can see here we're still continuing on with the geometry theme. But if you were told that two figures are congruent, what that meant is those figures were the same shape. Usually they were triangles for what we dealt with in module 6. So they were the same shape. But not only were they the same shape, but they also had the same size. So we can obviously have multiple triangles. Those are technically the same shape, but they're not necessarily going to be the same size. I could give you a little triangle and a big triangle. Those are not congruent. They're the same shape, but they're not the same size. If they're congruent, then we know they're not only the same shape, but they also have the same angles and the same lengths or same degrees. What we're going to be dealing with in this module a little bit more, we'll still deal with congruent. We're going to deal with this word similar. So similar means that two figures that are similar have the same shape. So a triangle to a triangle, a quadrilateral to a quadrilateral, a hexagon to a hexagon, but not the same size, at least not necessarily the same size. All right, so similar means something a little different than congruent, so just be aware of that. Congruent, we'll talk about it now. Congruent, we use this symbol to represent congruent, so that should be familiar to us. When we start using similar here in a minute, the symbol for similar is just the little squiggly. So instead of the squiggly with the equal sign underneath it, we just do the little squiggly. Whenever you see this, this means that they are similar figures, okay? If you are told that two polygons, remember polygon is an old word from Math 1, at many sides, so triangle, quadrilateral, hexagon, pentagon, anything with more than two sides, basically triangle on up would be considered a polygon. All right, then there are two things that are true if we were told that polygons are similar. The first one, all corresponding angles are congruent. So very much like our congruent module, all the angles are corresponding angles are congruent. Yeah, that's just. I don't know. I didn't open up the big package, like 89-ish. So look for where it says this, Math 2, Day 3, or 6.3. Yeah. Oh, do you not? Oh, sorry. The pages get all messed up on these. I don't know how. I belabor this and that. And if you don't have a packet, everybody get a packet yesterday? We did make more copies yesterday if you need a packet. All right, then the other thing, so all corresponding angles are congruent. And then all of the sides, we're going to write this way, the ratio of the length of the sides are constant. We'll put that, or the same, however you want to put it. So a lot of words there. Go ahead and write that, and then I'll kind of show you with some graphs here what those then mean. So if I give you that, we have two triangles that are similar. So let me draw in two triangles that are similar. Clearly not congruent because one is bigger than the other. If I tell you that these are congruent, let's say that this is 1, 2, 3, and then this is angle or 4, 5, and 6. The corresponding angles, so once we identify how we can identify what angles are corresponding, let's say angle 1 and angle 4 are corresponding, they're going to have the same degree measure, exact same degrees. If angle 2 and angle 5 are corresponding, they have the exact same degree measure. That's what statement number 1 is saying. What statement number 2 is saying, and this is the one that's a little bit harder, draw in, I think I did this earlier, I liked it. So draw in a triangle that looks like this, and then draw in, no pun intended, but a similar triangle that's just bigger. So basically the same size, but just a bigger version. Label this side A3. And then notice what our corresponding sides are. here's the small side. If I ask you what the corresponding side is in the big one, hopefully we would see that this side corresponds to this side. And let's label this side 6. Notice how the bigger one is twice as big as the smaller one. So what that would then mean, and this is what this second statement is saying, the ratio has to be constant in all of the sides. So if I then tell you that this is a length of 4, what would this corresponding side's length have to be? 8. Because if this is double 3 to 6, then the 4 would get doubled to be 8 and 8. If I then tell you that this side is a 10, not a 10, sorry. Yeah, see, I was thinking ahead. I do that a lot. What does the bigger side then have to be? 10, because it has to be twice as big. So that's what we mean by it has to have a constant ratio in the length of the sides. So if one side is double of the other, all the sides are double of their corresponding sides. Okay. When we start talking about a similarity ratio, let me write that down. That's actually what I wanted to write down here. Sorry, I read my notes on this. So this is the ratio of the length of the sides in two similar polygons. So write that down, and then we'll talk about what this would mean based upon the one that we just did. At some point, we won't necessarily do it today, but I'm going to ask you, what is our ratio from one triangle to the other? So if I did from here to here, some of us are still writing, so hold on a minute here. I'll wait till it looks like we all got that written down. All right, if I went from the small triangle to the to the big triangle, and I ask you what is our ratio, notice how this is 3 to 6. Let's write it as a fraction. Doesn't 3 to 6 reduce down to be 1/2? So isn't this triangle, these lengths, isn't 3 1/2 of 6? And 4 is 1/2 of 8. 5 is 1/2 of 10. So our ratio, if we're going in this direction, so keep that in mind. So if I'm going to go from small to big, we would say our ratio is 1/2. We can also write that as 1 to 2 with the little colon there. We can use the words, all those options we talked about yesterday, the colon, the word 2, or a fraction is 1 to 2. However, eventually, let's say I give you this and I say, all right, what's our ratio from the big to the small? Now this is different, correct? Because isn't this one now 2 compared to 1? So that would just switch that around. So we won't change this here, but we always want to know which one are we starting at and which one are we going to be going to, because then that's going to change the order of our ratio. Okay. All right, the similarity statements. So here's what I want you to do here. We'll do this as a triangle. So write triangle, and then I'll have you do ABC. And then we're going to use that little similar sign. So I'm going to tell you that triangle ABC is similar to triangle D. Let's not do D. Let's do XYZ. Then underneath that, let's draw in some figures like we did before. So actually, let's draw in the same look and shape we dealt with before and call this A, B, C. And then draw in a similar looking triangle, but just bigger here. And we'll call this X, Y, and then Z. What the similarity statement does, it gives us a lot of information about our congruent angles, our corresponding angles, and our corresponding sides. So if we look at our graph, notice how the A, B, and the X, Y appear to be corresponding parts here. Look at their order in the similarity statement. A and B are the first terms listed here. X and Y are the first terms listed in the second one. That order tells us which sides correspond. All right. If we do, let me erase these. Look at the corresponding sides here. So this is BC, should correspond to YZ. Well, look at their order. Notice how BC are the second and the third, and then it corresponds to YZ. Well, that's the second and the third variable in the similarity statement. And then the last one, AC and XZ, those correspond to each other. And notice how they're related to each other. AC are the two bookends, the first and the last. XZ are the bookends here. So that's how if I don't give you the graph at all, we can just look at this statement right here and identify what our corresponding parts are. All right. So with that in mind then, and this I'll have you write in on this line, if I ask you, remember all corresponding angles are congruent, right? That's one of the things that's always true when we have similar figures. So if I now in this second line here ask you angle A would have to be congruent to its corresponding angle in the other triangle. What is angle A's corresponding angle in the XYZ triangle? Alexis? X. And it's because A is listed first here, X is listed first here. That's how we know those correspond to each other. So if we then just go with that line of thinking, doesn't angle B have to be congruent? B is second. It would have to be congruent to angle Y. And we can see that in the visual down here as well. A and X corresponded to each other. The B and the Y corresponded to each other. And then the last one, angle C, would have to be congruent to angle Z. All right. So with those things in mind, now we're going to set these up and answer some questions with this. So let me create a little bit of space. All right, so example one, if you look, we now have polygons. We have quadrilaterals. Those are four-sided shapes. You were told, and again, the order is important here, that ABCD is similar to EFGH. Complete each statement. So what the first one is asking you to do is to find the measure of angle E. So angle E is over here. It's unmarked. And we want to figure out what degree measure does that angle have. Remember what we mentioned earlier, corresponding angles, as long as we know these are similar to each other, which we do because of the symbol, corresponding angles are congruent. So if we look at the similarity statement, here's angle E. Doesn't angle E have to be congruent to angle A? Because those are corresponding. So look at angle A. Don't we know the measure of angle A? Yeah. So whatever angle A is has to also be the measure of angle E. So angle A is right here. It's 53 degrees. That means angle E must also be 53 degrees. All right. All right, and then angle B, or letter B, angle D. I messed this up earlier today, going a little too quick. Notice how this says the measure. This doesn't say the measure. Notice how there's an equal sign here. There's a congruency statement here. All we are asking you to do in this one is look at angle D. So figure out whichever figure has angle D. Look at the other figure and tell us what angle D would have to be congruent to. We don't need the degree measure. Angle D would have to be congruent to angle what? And then just write that letter. All right. Gael, what do you think?
Angle A.
Good. And how did you do that?
At the end, it's like it says D, and then the other end it says A.
Good. So he used the congruency statement right here. He didn't look at the graph at all. He just knew that angle D was the fourth letter in the congruency statement. So the fourth letter and the other one is an H. Those two are congruent to each other. Good. And then he said both on the bottom right-hand corner. So he knew that's also graphically how we would match those up. Okay. All right, now, these a little harder when we start setting up these proportions. So the angles, I think most people are going to understand. The proportions get a little bit wackier for some people. So what we're doing first, look at where we have a completed fraction. So here's our complete fraction here. So understand then what we are comparing in this AB to the BC. So I have taken AB, and we are comparing that to the BC. So what we've done is we've taken the first two terms in the first quadrilateral, And then the second and third terms in that first quadrilateral, that means the ratio over here better be the exact same pattern in the other polygon. A and B are the first two terms. Notice what the first two terms are in this one. That's E to F. So this would have to be E to F. Notice the B and the C were the second and third terms. Notice how the F and the G were the second and third terms in the second. So those correspond to each other. All right. We can rearrange these in all kinds of ways. As long as the one ratio on the left and the ratio on the right mean the same thing, then you can rearrange them however you want. See if you understood that, because these are the ones I get a little worried about. These are the ones that typically people are going to have a harder time with. Try to find what that denominator would need to be. So if we did AB and EF equals AD over what? And I could have talked about in C, and actually, when I did it in first period, we did it with the graph actually. So you can use the graph or you can use your statement. Both of them are valid. It's just the graphs sometimes. The graphs get a little bit harder. Let's say I start rotating this around a little bit, and they're not perfectly matched up. Or you can kind of just look and see, like Gael said earlier, bottom right hand corner, bottom right hand corner. Well, what happens if we start rotating those? That's why it gets a little bit harder. But with these, the way that they currently are, you could really use the graph as well, or the statement. Okay. Got something in our head at least, whether you wrote it down or not. Jake, you're gonna go out on a ledge here. I honestly I didn't look and I don't remember what it was. So give it to me and then we'll see if you're right or not. EH. I don't know. So let's see. Jake says EH. It's not letting me write down. So
it's right here on the line A.
Oh yeah, there it is up here. What the heck? Let's do this. It didn't like me rotating that figure, I think. All right, let's try. All right, so Jake says EH. Do we agree with that before I even look at it? You're getting some good affirmative nods, Jake. All right, so he did AB. I'm going to do this with the graph just to show we can do it with the graph as well. So AB, and then got compared to EF. So he went the bigger one, the left-hand side on the big one. That's this part, and he compared it, or this fraction compared it to the left-hand side on the small one. So when we now go to the other one, AD, let me do this one in black. AD is the bottom of the big one. So we would be looking for the bottom of the small one. So if I come over here, the bottom of the small one is EH. So that is good. Is that how you did it, or did you use the statement? Did you do the graph?
Yeah.
Okay, so he did use that graph. We could have used this here too. The first two terms were compared to the first two terms in our similarity statement. And then we took AD, which were the bookends, the first and the last one in that first one. So then we've got to do the first and the last one in that second one, and that just happens to be the E and EH also. Okay, so whichever one you prefer. This long term is probably the safest. Just so when we start rotating figures, this will be your easier bet if you have that statement. All right, number 2, do A and B real quick. A and B should be hopefully nice. And then C is hard. And we haven't necessarily done C yet together, so we'll do C together. And once you have A and S, I would just hang tight on RS, the length of RS, because we haven't necessarily done one of those yet. All right, our angles. The reason the angles should hopefully be nice is we've dealt with this idea a few times now. It goes back up to here, what I have circled. If we have similar polygons, all the corresponding angles are congruent. So if we understand that all corresponding angles and similar polygons are congruent, that's how we want to handle those first two angles. So measure of angle A, you're not given. That's what we're asking it. But if we look here in triangle A, B, C, A is the first listed term. So A would have to have the same degree measure as angle Q. If we go over to angle Q, don't we have angle Q? And angle Q is 46, so this has to be a 46 degree angle. Okay. And then let's label that in here. All right, angle S. Anybody want to walk us through that one? Get that? Get through there. Break souls. O and S. It's the first time we kind of done this. Angle S is what we're looking for. So we're trying to find this angle right here. It's not marked. And again, there's some different routes you could take here. So if your line of thinking is maybe a little different than mine, still probably valid. To me, angle S has to be congruent to angle C. So angle C is unknown. However, old idea, it's been a while, but this is, I think, one of the theorems that everybody had a really good handle on when we did it. How can we figure out what angle C is, Alexis?
You can add up 46 and 53, and then subtract that, or do 180 minus the total.
Good. So inside of a triangle, they have to add up to be 180. So she said we can add these up. So I'm going to write it like this just so we see it. If we add them up, though, that's 99. Subtract the 99 away from the 180. And then that should leave us. Did you get it, Alexis?
No, I did it wrong. I'm trying to get it down.
Okay, that's okay. Yeah.
81.
Good. And then that ends up being 81 degrees here. So if we then know that angle C is 81, remember, C is the third listed term here, as is the S that we are looking for. So S has to be the same degree measure as C, so this must also be 81 degrees. Okay. All right, so those are our angles. Those, I think, long term, as you see a few of these, I think we'll handle those pretty well. The lengths of the sides are the ones that get a little bit sketchier here. In order to figure this out, notice all of these proportions that we have set up here. So this proportion and this proportion. Once we have the proportion, this is all your homework last night, right? You had a bunch of these. And we know once we have a proportion set up, they're easy to solve. You crisscross, multiply, you solve. All right, easy. What we need to do to solve these is we're going to use that idea that each side is the same ratio to a corresponding side in the other triangle. So what we want to do is set up our proportion. So proportion is simply one fraction set equal to another fraction. So when we look at our two shapes, the key to you setting one of these up is we need to come up with a corresponding fraction where the corresponding sides are known. So what I mean by that is, it wouldn't do us any good to do AB, because do we know the length of AB at all? No, you're not given that. We do know AC is 6. What we would like to know is, do we know AC's corresponding side? So let's look at our similarity statement, because now notice how these are rotated a little bit. So it's not quite as easy to identify what our corresponding sides are with this. So if we look at our similarity statement, though, AC is the first term and the last term. Look at the first and the last term of the second one, Q and S. Do we know the length of QS? Yeah, so that's a good thing. So what we're going to set up, I'm going to use variables first. I'm going to take the length of AC and I'm going to compare it to the length of SQ, because those are corresponding sides. Also understand, let me try to sneak this in here without butchering it and writing it too big. I have the big triangle on top and I did the little triangle on the bottom. So when we set up this next fraction, we better have the big triangle side on top, and we better have the little triangle side on the bottom. What we have to put in is RS somewhere. So notice how RS is this side of the small triangle. So if we want RS, the little triangle goes on the bottom. We're going to put our RS here. And then we need the corresponding side of RS and the big triangle here. So write that down real quick. What do you think is the big triangle's side that corresponds to RS? And just use variables right now. All right. RS is here. So the corresponding side should be what? Vicky or Victoria?
BC.
Good. The second and the third term here, which is BC. So that's how we can set up one of these proportions. This was our key. The reason this one was key is we know both of them. We want to have a complete fraction. So now let's actually throw in some values. Don't I know that AC was 6? So put the 6 right here. SQ we know. SQ was 5, so you're going to let that be a 5. BC we know. That's 18. RS we don't know, so I'll let that be the X that we need to solve for. That's the variable that we're trying to find. That's the proportion that we can then get set up for that. Once that's set up, my guess is most of you with this homework yesterday or the notes thought this was pretty nice. You just crisscross, multiply those. Well, we better hurry. 6x is going to equal 90. And then divide by 6, and we get x to be a 15. All right. These proportions are the ones to be careful of. Those are the ones that we're going to need some practice on, just to make sure we're setting them up correctly. Once you have them set up, they're easy to solve, though. Okay. All right. You don't have homework tonight because we didn't get enough done. So we'll do 3, 4 tomorrow, and then we'll get started on the homework a little bit together in class tomorrow if we have some time. All right. So you have the homework due tonight, but from these set of notes, there's no homework. Okay. All right. We'll see you guys. Have a good day. Good luck tonight, Mason.
Thank you.